Very interesting. And we can switch to the next speaker, and who is Davide Marcato. Davide Marcato will speak about phase behavior of semiflexible polymers on a lattice by Linfield and Monte Carlo simulations. And about CV, we can say that he studied in Padova, and he did the master thesis with Amos Maritan on nanometric scaling biological and ecological systems. And then he moved from Padova to SIFS and Trieste, where he studied lattice field theories for polymer systems that are related to the topics of the seminar today. Nowadays, he is in Lisbon, and where he's working on with Pablo Sartori. I don't know the subject actually of his current research. So please, Davide, you can start.
Yeah, so thanks for the introduction. Hello, everyone. Yes, Giuseppe was saying, I'm now working as a postdoc at the Gulbenkian Institute in Lisbon. But actually, the things that I want to present today are from the first project that I carried out during my PhD in SIFS. And the topic is phase behavior of semi-flexible polymers on a lattice. So let me start with a little bit of biological context. Basically, the motivation behind this work came from protein condensates. So this is a picture taken from a paper by Monica Fuchsreiter and Michele Vendruscolo, in which they explain that if you look into a cell, a living cell, you may find a protein in one of these three states. So the first one is the most famous, it's the native state. It's the one that AlphaFold is now so good at predicting. So basically here you are in a situation or in a phase in which every protein is by itself. There is not really a protein-protein interaction. And each protein folds in such a way to minimize its free energy. So since every protein is by itself, this is a non-condensed, let's say, phase. Or if you want, it resembles a sort of gas, a gas of proteins. But then, contrary to what was the common belief, this is not the only state in which you can find proteins in a living cell, because actually you can also find them in condensed phases. For example, you can find them in droplets, which are a sort of condensed phase but characterized by a disorder. So there is no specific structure, let's say, to any of the proteins participating in the droplet. And so for this reason, it resembles a sort of liquid. And then there is another condensed phase, which is the amyloid phase, which is instead characterized by structural order. You can see from this picture that all the proteins are sort of aligned. And because of this order, it resembles a sort of crystal. So in this paper, they explain this phase behavior, but on a very qualitative, let's say, level. So if one wanted to be more quantitative on this sort of system, you will soon encounter a problem, which is the fact that basically you have to determine a phase diagram in a parameter space which has a lot of axes. Because, for example, you need to check what happens when you change the temperature or the protein concentration or the stiffness of the molecular backbone, the intermolecular interaction, the pressure, and so on and so forth. And so the idea that we had was, okay, maybe we can provide a mean field theory, simple theory, analytical as far as possible, that can help somehow in the navigation of this parameter space and can serve as a basis for more detailed computational studies. And so in order to provide such a simple theory, the first thing that we have to do, of course, is a drastic simplification. In particular, we approximate an actual protein with all its atomistic details to a much simpler structure, which is a homopolymer. It's basically a sequence of units, which are called monomers, connected by bonds. Okay. And this simplification would actually permit to use all the tools of polymer physics. Okay, so the model that we propose is a lattice model. So basically, we work on a hypercubic d-dimensional lattice with n sites in total and with periodic boundary conditions. On this lattice, we are going to place our polymer chains. These chains have three important features. They are open, first of all, so it means that you cannot have closed rings. They are linear in the sense that there are no branching points. And most importantly, they are self-avoiding, which means that there is, let's say, an excluded volume interaction between the monomers. And this is enforced in the model by saying that you can have at most one monomer per lattice site. And then we indicate with NP the total number of polymer chains and with NB the total number of polymeric bonds. So the bonds between consecutive monomers. And for mathematical convenience, as will be clearer later, we initially work in an ensemble in which nor the total number of polymer chains nor the total number of bonds are fixed. So basically, you can have whatever number of polymeric bonds arranged into whatever number of chains. So these are three illustrative configurations of this ensemble. So you have the first one on the left here, in which basically you have 3 chains and 4 bonds. On the second one here, you have the same number of bonds, but they are arranged differently, and so in total you have less chains. And instead here you always have 3 chains, but there are more bonds, and so on average the chains are longer. So we are considering the ensemble of all these possible configurations. And already from here you can see a very important point, which is that the system is in general polydisperse, which means that not all the chains have necessarily the same length. Okay, and now we introduce an Hamiltonian. It's a simple Hamiltonian made of only 2 terms. So the first term is this one, epsilon A NA, and NA is the number of angles or 90-degree turns. They are highlighted in blue in the figure, like this one or this one. So it's when a chain makes a turn. Okay, and epsilon A is an energy penalty for making such a turn. Okay. So basically this term in the Hamiltonian is there to make the chains somewhat stiff or semi-flexible. And I mean, this term was introduced because semi-flexibility is a peculiar feature of biomolecules, proteins included, and so we introduced that in the model. And then the second term is instead the nearest neighbor interactions. So basically, whenever you have 2 monomers, non-consecutive monomers occupying neighboring sites, then there is an interaction. Ni is the number of such interactions. They are highlighted with dashed red lines here in the figure. And for each of these interactions, you have an energy minus epsilon I. And since epsilon I is a positive parameter, we are assuming basically that the interaction is always attractive. Okay. That's it. This is the model. And our goal is to compute the partition function, actually the grand canonical partition function, because we are in this ensemble in which the total number of chains and the total number of bonds are not fixed. And so here we have to compute this Z, which is the sum over all possible configurations. And here we introduce two additional parameters, kappa P and kappa B, which are respectively the polymer fugacity and the bond fugacity. So basically the role of these parameters is to assign different statistical weights to configurations that have different numbers of polymers and different number of bonds. So for example, if you push kappa P very high, you are favoring configurations in which the number of polymers is large. And the same with kappa B. So now the question is, how do we compute this object, this partition function? And in order to answer that, I need to take a small detour to a seemingly unrelated problem, which is spin models. In particular, I will talk about the ON spin model, which has a very simple, let's say, definition. So you have a lattice in whatever dimension, doesn't matter. And on each lattice site, X, there is a spin vector, S, and this vector has n components, small n components. And there is a constraint. And the constraint is that the square modulus of the spin must be equal to n, to the number of components. So for example, these are examples on a one-dimensional lattice. So for n equal to 1, you recover the Ising model, standard Ising model. For n equal to 2, you have that the spins are constrained on a circumference of radius square root of 2. For n equal to 3, you would have a sphere of radius square root of 3, and so on and so forth. And then the Hamiltonian here is the standard, let's say, Ising-like Hamiltonian, where there is an interaction between neighboring spins that favors the alignment. And kappa here is the interaction parameter. Okay, this is the model. Now, you can define in this model a trace operation. We indicate it with angular brackets, in which basically you integrate overall possible spin orientations with the constraint that the square modulus of each spin must be equal to n, which is enforced by this delta function here. And once you have defined this trace, you can compute all average quantities, let's say. The interesting fact that was observed for the first time by Dejean in the 70s is that if you do this, if you take this ON model in the formal limit in which n goes to 0, so the number of components of the spin vectors goes to 0, then this equation holds. So here on the left, you have basically the partition function of the spin of the ON model, because you are taking the trace of the Boltzmann factor. And then you take the limit for n going to 0, and on the right, you obtain this expression here, but in particular, there is this term, NL, and NL is exactly the number of self-avoiding rings of L steps. So basically, on the left, you have the partition function of the spin model, you have the magnet, let's say. On the right, instead, you have a quantity which is related to self-avoiding rings on the same lattice of the spin model. And the limit for n going to 0 ensures that there is a mapping between these two systems. So for this reason, this is called the polymer magnet analogy. And now the idea, I mean, this was done by Dejean in the 70s, but then it was also generalized by Descloiseau shortly after for systems with multiple chains, and then later by Doniak and collaborators to introduce for a single chain the semi-flexibility. And what we did was actually to generalize it even further to account for multiple chains which are semi-flexible and also for the nearest neighbor interaction. Okay, so that's what we did, and we were able to show that our partition function, the grand canonical partition function Z of our model can be exactly expressed in this field-theoretic representation. So basically, you have an integral over some variables, and these variables are fields. Okay, so psi of x is a scalar field in correspondence of lattice side x, and instead this phi mu is a vector field, an n-component vector field. And here at the beginning, you have this limit for n going to 0, which is reminiscent, let's say, of the formalism that we have used to obtain this expression. And then here you have an exponential of a function, a, which is the effective action of our field theory, which has a, I think, not simple, but not even too complicated expression. However, the point is that the exact expression, I mean, up to this point, everything is exact, but the expression of A is too complicated for the integral to be computed directly. And so the idea is to approximate, and in particular to perform an expansion around the saddle point. So basically you minimize the action, and then you expand around the minimum of the action. And if you stop at first order, this is basically the approximation that you get for your partition function. So you will have saddle point equations, which you will solve numerically, and then you plug the results back into the expression of the action, and you have your approximate expression for the partition function. Okay, now once we have this approximation for Z, we decided to test it. So for example, one thing that you can do is to compute the polymer density, Phi, so which is let's say, the average number of polymers divided by the total number of lattice sides. Or you can compute the bond density, Phi, which is the average number of bonds divided by the total number of lattice sides. This you can do with basic, let's say, statistical mechanics relations. And then in order to validate our prediction, we performed Monte Carlo simulations of the model in the same ensemble, so in this grand canonical ensemble, with a very simple, let's say, Monte Carlo scheme in which you simply insert or remove bonds from the configuration. But for the sake of time, I mean, this is really a simple algorithm, so for the sake of time, I will move on directly to the results. These are the results that we obtain. So on the top row here, you have fully flexible chains because epsilon A, the bending stiffness, let's say, has been set to 0. And also epsilon I, the nearest neighbor interaction, has been set to 0. So in this case, there is only, yes. There is only entropy, sorry, only excluded volume. And then here on the left, you have Phi P, the polymer density as a function of kappa B, the bond fugacity. And on the right, you have the bond density, Phi B, again as a function of the bond fugacity. And different colors refer to different values of the polymer fugacity. So blue is for low polymer fugacity, which means that you want as few chains as possible. And instead, the red is for large polymer fugacity, so you want as many polymer chains as possible. The solid lines are the mean field results, and the symbols are the Monte Carlo simulations. So you can see that there is a satisfactory agreement between mean field and simulations. Also in the case of semi-flexible chains. So now here we switch on epsilon A, we set it equal to KBT, because it's a physically meaningful value. And also in this case, you can see that there is a satisfactory agreement, let's say. Here instead, what we did was to switch on the nearest neighbor interaction. Now epsilon I has been set to KBT. And you can see that in this case, there is a qualitative difference with respect to the previous case, because now there is a phase transition. In particular, you go from, when you are at very low fugacity, you are basically in a gas phase. So there are very few polymer chains and they are very, very short. The lattice is basically empty. And then at a certain point, you hit a critical value of the bond fugacity, and all of a sudden, your lattice is filled with polymers. And this is true also for semi-flexible chains. So here we have both the semi-flexibility and the nearest neighbor interaction. And again, we see the same behavior. And also Monte Carlo simulations showed the presence of this phase transition. Okay, so we were quite happy with, let's say, with the results of the mean field in comparison to the Monte Carlo. However, we are working in this weird ensemble in which you don't have a direct control on, let's say, the number of chains and the number of bonds, but you can only control them through these fugacities or these chemical potentials. So our idea was to try to switch to an ensemble in which you fix the total number of polymers and you fix the total number of bonds. So basically, we want to go to the canonical ensemble, and in order to do that, you basically compute the gram potential, and then you do a Legendre transform, and in doing that, you get the Helmholtz, if you want, free energy per lattice site, which is given by this expression here, where now we have introduced some new quantities. So the phi is the sum of the polymer density and the bond density. So it's the total monomer density. This is a relation that is always true if you have linear chains, linear open chains. Then this L here is the average number of monomers per chain. So if you want, is an average length of a chain. And I say average because when you do this Legendre transform, you fix the total number of polymers and you fix the total number of bonds, but you have no control on how the bonds are arranged into different polymers. So the system remains polydispersed even after this switching to this canonical ensemble. And then you have this Q of beta here, which appears only here, which is a quantity that, let's say, contains all the contributions of the bending rigidity. Now, let me go a little bit into the details of this. So for those of you who recognized it, the first part of this formula is exactly identical to the Flory-Huggins formula, which is a cornerstone in the study of phase separation processes, condensation, and so on and so forth. So it was quite surprising to find it as a, let's say, as the zeroth order of the expansion around the saddle point of an exact field theory. Let's say it was not trivial from the beginning, I would say. And then here you have a correction. And this correction is actually linear in the monomer density phi. And this is the fact that there is this linearity has very important consequences for the phase behavior of the system, for the condensation, let's say, of these chains. Because if you want to study phase separation or condensation, what matters are only the convexity properties of the free energy. So basically, what you have to look at is the free energy, the red curve, and the convex hull of the free energy, which is the dashed black curve. And so when the two coincide, there is no phase separation, there is no condensation, nothing. But when the two do not coincide, then you have phase separation, and the system separates into a condensed phase where all the chains are very dense, and a depleted phase in which the chains are very sparse, let's say. But the fact that our correction is linear implies that from the point of view of phase separation, we reobtain the Flory-Huggins phase diagram, even though this phase diagram was originally obtained by Flory and Huggins for a monodisperse solution of fully flexible chains, whereas we obtained the same thing for a polydisperse solution of semi-flexible chains. And the idea is that these two things might be related to one another. So to conclude, we have provided, first of all, an exact field-theoretic expression for the grand canonical partition function of the system. Also, we have provided an in-field approximation, and we have shown that we get predictions which are in good agreement with Monte Carlo simulations. And then we have also shown that since the correction that we get is linear in the monomer density with respect to the standard Flory-Huggins picture, liquid-liquid phase separation seems to be unaltered by semi-flexibility for a polydisperse solution. For a monodisperse, we don't know. Let me finish with the acknowledgements. So first of all, I remember that this is the work that I've done during my PhD in SIFS, and I want to thank all the people that participated in this project. In particular, so Angelo Rosa was my supervisor in SIFS, and then Achille Giacometti from the Ca' Foscari University, and also Amos Maritan from the University of Padova. And I thank you all for your attention.
Thank you, Davide, very much. And yeah. And questions? I can start from a curiosity. And
yes.
You showed an effective action, which
yes.
I think should probably generalize the usual 5 to the 4th Landau free energy. So in the case of standard self-avoiding polymers with any other interaction or other things, the vector should be the standard vector appearing in Landau-Ginzburg's double well free energy. So my question is, what is psi, if it is possible to...
Psi, this one here.
Psi, the scalar, yeah.
Yeah, the scalar field is necessary if you want to introduce the nearest neighbor attraction. Because basically this is... if you don't want nearest neighbor attraction, you can forget about this field. You don't need it. You only need the vector fields.
Because also the vector field has a nearest neighbor attraction for constructing, I think. So, yeah. There is also, okay, yeah.
Yeah, this is only for let's say, for having the so-called poor solvent conditions. So when on top of excluded volume, you also have this short range attraction.
No, that was the question. Okay, thank you. Other questions? My second question, so I can ask you. If polydispersed chains are realistic for protein, you started from protein phase diagrams. So my question is that if polydispersity is realistic for real system like proteins, or you don't know?
So I would say that in general, it's more realistic to talk about a polydisperse system than a monodisperse system for let's say, for a real biological solution such as this one. because you will never have exactly, let's say, all the same molecules and all, let's say, with the same structure. However, let's say, in our model, polydispersity is sort of annealed, because you are considering all possible ways of arranging the bonds into different chains. Whereas I mean, what would be more realistic was to have, let's say, a fixed length distribution. So you somehow fix the you say, okay, my system is polydisperse, and there is a certain length distribution which is fixed, and then you start working with that. But with our model, we could not do it.
Okay. Clear. Thank you. Other observations? Or I don't see. I don't see any. And yeah, so I think we'll stop here this session, so the 2 seminars of today. And thank you very much for these 2 excellent presentations, extremely clear and interesting for the results too. And so see you in the next young seminar, Italian Statistical Society seminars. So ciao Achille, ciao to everyone.
Ciao a tutti.
And thank you very much. Thank you very much,
grazie.
Davide e Riccardo. Grazie. Ciao,
Grazie a
Amos.
voi.
Ciao.
Arrivederci, buonanotte.
Ciao. Molto interessante, grazie.
Ciao.
Ciao a tutti. Ciao.